In this class, let us try understanding fuzzy sets in a more practical manner. Let us take the example of two crisp sets. So crisp sets are your regular sets, and let us have a universal set which has 4 elements 1, 2, 3, 4, and another set called A which has 2 elements 1 and 4. We can also write A in another format like this. Now this format might be new to a lot of you people, so please try focusing a bit here. Now 1 is an element which is present in A, which is also present in your universal set. So what I'm going to do is attach another small 1 here. So this says that, okay fine, this 1 is present inside the universal set. Now with 2, which is also present in the universal set, is not present in my set A. So I'll associate a value of 0 with it. Similarly with 3, 3 is present in universal set, it is not present in A, so it will also have a value of 0. With 4, it is present in both A and U. So for this, I will associate the value 1. So what do these 1 and 0s indicate? They sort of tell me whether this element is present inside U or not. So it's sort of what my membership value is doing. So this is the element, the left coordinate is the element and the right coordinate is the membership value. This notation is pretty much what we use for fuzzy sets. So as I have already told you, fuzzy sets are extensions to it. Now this is the way you usually define your fuzzy sets. So X here is your element and mu fx, mu subscript fx is your membership value. So f is the set and x is the element. And as I already told you, the membership value always lies between 0 and 1. Now let us take a small example. We have f as something like this. It has 4 elements. So instead of having zeros and ones as the membership values, we can even have fractional values. You can have 0.2 and 0.4, 0.7, 1. So over here 4 is the only element which is totally present inside the universal set, and all the other elements, they're partially present. Now if you have 0 for any of the elements like this, like if you have a 2, 0 or 3, 0, you can skip writing those elements. You need not represent them in this final representation of f. Now let us try learning more about these membership functions. Let us look at a few properties of them. So let's say we are looking at a problem where we want to find out numbers which are close to A. So A is a number, we want to find out any numbers which are closer to A. So if that is the case, the membership values of all the values which are at A will obviously be 1. And mu fi, that is the membership value, is symmetric with respect to x. So if we have a graph like this, so x is, let's say, 0.5. So 2 is where my A is. So this is my A. And let's say my x is 0.5. So if this is the case, so if I map 0.5 on this, so from 2, if you go left, 0.5 occurs at 1.5. So this is the direct mapping of it. And similarly, from 2 to the right, if you go 0.5, you will reach 2.5. And if you look at both of these mappings, the y coordinates should always match. So that is another property that we have with the case of membership functions. So that is what 2 is saying. And mu fi decreases monotonically from 1 to 0 with increasing difference a minus x. So what does this indicate? Now if you look at this thing, a is what we have here. It is 2 right here. The membership value is basically 1 and the x coordinate is 2 or a here. Now if you look at this part, all the values if you go either towards right or if you go towards left, they always keep decreasing. So that is another nature that we have with membership values. The highest value appears only at A, it doesn't appear at any other parts, and all other parts just have a decreasing trend. So that is as far as the properties of membership function go. Now let us look at a generalized function for the representation. So this is how you would represent this curve here. So you could have continuous membership functions. So you need not always have discrete values like what we have seen. You can even have continuous values like this. So this is just one example. We'll look at more in the future classes. So I have a small assignment for you guys. So if you guys understood this topic so far, what I want you guys to do is take a look at a small example that you have in your textbook. It's a very beautiful example. It helps you understand how the membership value changes when you're looking at different sets. It's on page number 347, and you'll be writing out different membership functions for child, teenager, young, and old. They're already given in the textbook, so you need not worry. So what I want you guys to do is write out those membership functions and then understand how the graph is appearing. The graph is present in page number 348. It's figure 10.2. It has a name, graphical representation of membership functions. So I want you to map out the values which are present in 347 to the graph which is present in 348. So that's your first question in third assignment. So let us move forward to fuzzy set operations. We basically have three operations in fuzzy sets. There are more, but these are the three basic operations. The first one is complement. So it's sort of different from the complement that you have seen in your regular sets. So let us try understanding this. So U is my universal set and A is a small fuzzy set that I have here. So what is my complement of this A? If I want to find out the complement, so what does it actually say? It wants me to find out all the elements which are not present in A. So if I have a look at it, I have 3 and 4 here. So our general intuition is we need to introduce 1 and 2 as well. But since this is a fuzzy set, we also need to define the membership values. So 1 is totally not present in A, so I associate a membership value 1 in its complement. Similarly with 2. With 3, I already have a membership value 0.7, so in the case of complement, I'll be using 0.3, so whatever is left from this 0.7. Similarly with 4, I have 0.3 in A, so I'll use the remaining part 0.7 in the case of complement. The second basic operator we have is a union. So let us define another small fuzzy set called B, and that is this. Now if I were looking for a union of these two, I need to look for all the elements which are present in both A and B. So the distinct elements I have are 2, 3 and 4. So 2 is not present in A, so I can directly write down whatever is present in B. So it's directly 2, 0.3. With 3, I have a clash. It is present both in A and B. So over here in A, the membership value of 3 is 0.7, and in B, the membership value of 3 is 0.8. So if I were to club both of them, 0.8 is maximum. So I'm going to use that value in the case of union. Similarly with B, with 4, I do not have any 4 in the case of B, so I'll use whatever is present in A. And the next operation we have is intersection, and intersection is where you take the minimum value of whatever values are intersecting. Now if you look at both A and B, the only intersecting value is 3. That is, the only common value is 3. And out of these two, the least membership value is 0.7. So I'm going to use that here.